Mike Stish. I'm editor-in-chief of Hackaday. It's really nice to be back with you today, and I have the honor of introducing our first keynote. We can all sense gravity. So, all we have to do is like grab something and drop it. But really characterizing that becomes difficult. And like still air and a light breeze, gravity can actually fluctuate. And so scientists set out to measure this more precisely about 2 decades ago. And in order to do so, it takes things that are really large in scale, really low in temperature, really high speed, and of course, ridiculously precise. Oh, and you need some software to run them as well. And in this case, a custom flavor of Linux is part of that. Dr. Keith Thorne is a group leader at LIGO, Livingston Observatory. So LIGO is the instrument that's being used to make these measurements. It stands for Laser Interferometer Gravitational-Wave Observatory. He's part of a team who is literally observing ripples in space-time, and I just can't believe how cool it is to say that. It's my pleasure today to introduce Hackaday Remoticon keynote speaker, Dr. Keith Thorne.
Thank you very much for that introduction. Oh, yes, I'm Keith Thorne. First, it actually has been about 40 years we've been trying to do this, but who's counting? Thank you very much. I'm actually here at the LIGO Observatory because someone set up the lighting so it works. And I don't have broadband at home right now due to a hurricane. Anyway, I'm going to start my talk, tell you about gravity and things that correct, like black holes, neutron stars, and all the great stuff we've seen and how the interferometer is. And then about halfway through the talk, I'm going to change gears and tell you that we're hackers too, and all the great hacks we've done in LIGO to make this work. Hope it's a little inspiration to you that even we, big scientists, we do it too. So I'm going to go and get over to my presentation here. Talks about LIGO, extreme instruments for extreme astrophysics. So first, I'm going to take you through something about stars. And stars are always interesting because basically it's a fight between gravity pulling the gas in and something pushing out. So I learned in astronomy that a star is pretty much just a balloon that's inflated by the photon pressure from the nuclear fusion core fighting against the gravitational collapse. That's sort of neat. But what happens when the lights go out? When you've used up all the hydrogen and the helium and whatever? Well, it depends on how big they are. If they're about the size of the sun, they end up being what's called a white dwarf. If they're up to 10 times as big as the sun, they sort of blow up stuff and then become something more extreme, a neutron star. And then if they're really big, they become a black hole. So what are these extreme things? Well, I'll mention with white dwarfs, we've seen them in telescopes. Basically, any star up to about 8 solar masses, you get a nova or a supernova. It blows off all the extra mass and gets down to 1.5 solar masses. But at that point, it's only 10,000 kilometers across. And in this case, the pressure is something called electron degeneracy. That means the electrons can't be in the same state, so they push, but they act like a pressure. We aren't detecting those with LIGO, though. But then there's something more extreme called neutron stars. And here you start with bigger stars, about 10 to 30 solar masses. They pretty much become supernova. They blow off all their other mass in a big shell, and they get down to like 1 to 2 solar masses. And they're much more extreme. They've blown all the electrons away. So it's just protons and actually just neutrons. All the electrons absorb into the protons. It's all neutrons. And it's only 10 kilometers across. And basically they get a very high spin, very magnetic field. And it's again, this Fermi, it's called Fermi degeneracy that keeps it from being collapsing. So those are pretty extreme. We've detected them. They're hard of pulsars, things like that. But you can get more extreme. Black holes. If you started at like 30 solar masses, you're going to collapse so fast, even the neutron ain't going to matter. And it's a prediction of general relativity that you're going to get down to black holes. And the collapse is so extreme that even light can never escape from the event horizon, which is about 30 kilometers or so, depends on the mass. That would be why we call it black. So it's a singularity of pure gravity. There are only like 3 parameters. It's how massive is it? Does it have a charge? Does it spins? So those are out there, but they're very hard to see, especially something that's black. You can only see it when you have other stuff with regular telescopes, but we set out to do it. So I mentioned general relativity. Einstein always comes in on this. So what did he say? The one thought Einstein had over 20 years ago was that you can't tell the difference between a gravitational force and the fact that instead of the force, if you think of like a sheet of rubber, instead of you being attracted, you have a big dump hole depression in the sheet of rubber due to the mass, and you're basically orbiting because space-time itself in 3 dimensions, not 2, is bent. And as a reminder, you say, well, I never have to worry about general relativity. Yes, you do. Do you like your GPS telling you where to go? Well, if we did not correct for general relativity from the GPS satellites to the curvature of the mass of the Earth, they'd be miles off. So you get really lost. So, and here's a video to show you the mass also bends space and time. Matter curves space-time. Space-time then guides mass, especially in lighter masses. So for instance, we have this very massive object, a little one comes in, orbits around it because space-time is curved, not because it's a particular gravitational force. And so that's how it works. Okay, we get that in your head that you're warping space-time, but something else comes up that's exotic. Is what if you have 2 black holes? This isn't that far near each other. This isn't so far-fetched. We now, astronomers estimate about 80% of stars are in binary systems orbiting each other. And all such orbits decay over time, and eventually they're going to merge. That is, if they do it before the universe ends first. And many times the universe will end first. But what if there's 2 massive black holes eventually, using the big word coalesce? Okay, they just smash together and combine. At the end, they are orbiting at 2/3 the speed of light. These are objects that like 20, 30 solar masses. It's 2/3 the speed of light. And they're warping matter around them. So they're pushing space-time, the other one's pushing, and they're getting in the way of each other. And when they coalesce, we've observed 3 masses of solar masses of mass goes right to energy. That is, you started with something that was total 53 solar masses, and you get done, it's only 50. Where are the 3 solar masses of mass? Well, E equals mc squared, so it went to energy. Well, it didn't go into light. And what it went into is massive ripples in space-time. You can sort of think of like you drop a rock into a puddle, pool of water, and ripples away. Okay, amplify that. And that's where all the energy is going. But how do you detect gravitational waves? Good question. So here's the only equation. We'll have equations after this. There may be another one. Okay, Einstein predicts this radiation. It has a funny thing, if you know about, there's like dipole radiation, like for antennas. This happens to be quadrupole. The only thing that really means is if you have a static object, it doesn't make gravitational waves. It's only you have 2 moving against each other that you get it. Acceleration. So we often express it in terms of something called strain, that is, how much is space-time stretched relatively. And we write these equations funny numbers, but the important part of this equation, h, is at 10 to the minus 20. So it's 10 to the minus 20, that's a decimal point, 20 zeros, times whatever the mass of the object is, and that's divided by a solar mass, so times how many solar masses it is, times how far away you are, that is this r, versus 10 megaparsecs. So it dies off pretty quickly once you get far away, which is a good thing because it tear you totally apart. So in fact, what happens when you get to the Earth? And this is why Einstein really didn't care much, because you never detect it. It's really small at the Earth from these objects. Okay, those zeros. Okay, meter to a tenth of a human hair is about a factor of 1,000,000. You divide that by 1,000,000. Divide that by 1,000,000,000,000. And you get to 10 to the minus 21 meters. Amazingly small. So that's why I said, this will never work. Don't worry about it. You'll never be able to detect them. You can't make a telescope to see this. But apparently, some scientists had other ideas. First one was Ray Weiss. He's one of our Nobel Prize winners. He was also one of our first hackers. One thing about his background, back in the 50s, he used to build audio circuits and sell them that would clean up the pops and clicks from the early hi-fi records. So he was doing his own circuits, how to filter this, and knowing how to do this helped him. But in this case, he actually assigned this as a homework problem, of course, to design some sort of interferometer, because lasers had just been invented 10 years ago. So laser interferometer is actually the ideal thing to use. But it took us about 30, 40 years to figure out how to do it. So here's Interferometry 101. And you even do that when you use laser rangefinders. It's the interference between one light wave and another. You send the light wave out, you split it in two pieces, it comes back together, and it's the interference between them. And so if you change the arm length of one, the light no longer perfectly cancels. There's imprecise cancellation of the waves. Now, if you're using white light at about, it's 100, you can do about 100th of a wavelength, or about 5 nanometers, 10 to the minus 9 meters. Lasers, you can do a lot better, because laser light is coherent. Fancy word for saying it's single phase, goes up and down coherent at the same time, and has one frequency. So if you control that intensity, the frequency, you can get much, much smaller, what we call displacements. You can measure much smaller distances, but you have to control for the vibration and everything. So that's basically how the LIGO interferometer works. And I'll take you through a little picture here, and you're allowed to go to sleep if you're not invested in fancy design. But we start with a laser. Right now, we run about 40 watts is the initial laser. So we do that, and we get the 40 watts, and then we recycle it. So you start with 40 watts. We have what are called mode cleaners that remove all the things that aren't the one frequency light we want, or scattered light. So we clean it. We have recycling cavities. Now we've built up the power, and the power matters because that helps you with something called shot noise, which we'll talk about later. So you want as much light as possible. So we're up to 5 kilowatts just in the input part. Now we create something called a Michelson interferometer as we split it and bring it back. And interesting, we always pretty much redo. The Michelson interferometer was used back before the start of the 20th century, or just add it, to figure out that there was no luminiferous ether. Say that 3 times fast. But that was the Michelson-Morley's. Basically, there's no stuff out there in space. It's just a vacuum. No preferential direction. So we do that, but then we make it better by having these arms called Fabry-Perot arms. Now, the LIGO interferometer is pretty big. Those arms are 4 kilometers long. It's pretty big. But you can make it better because you make it resonate, bounce back and forth with a half silver mirror almost 1,000 times. So instead of it being 4 kilometers, it's 4,000 kilometers effectively. And that helps with your precision as well. So, and also you're up to 750 kilowatts of power. And we'll come to that later. So then at the output, you bring it back down, you have more power, and they had this little thing called an output mode cleaner, which is only a box about this big, we diffuse silica glass, and we heat it a little to slightly change the resonance. So that's sort of the layout of it. And I won't go into too many details. We could go on for ages on that. But first I want to say, how extreme is the LIGO interferometer? Okay, I said 4 kilometers long. That means you can see it from any airplane. You can see it from space. because we have tunnels with concrete and they go out 4 kilometers, either through a desert or a swamp. Okay, so here's where the precision part comes in. We measure things to 1/10,000th the diameter of a proton, the one in the nucleus. That's how small that distance is that we're measuring. And you should go, how can you do that? Ooh, very careful. Okay, but you get very insane sensitivities. Like we have these resonant cavity has mirrors, which because we're physicists, oh, that's not a mirror, that's a test mass. And the reason it's a test mass is it is the thing that feels the gravitational wave. And that's what we're testing, is the distance between them. And it's about 40 kilograms, 80 pounds. If you get a little laser, your little pen-like laser, the photon pressure, not the heat, the little photons bouncing off the mirror are enough to control that. We can use a feedback loop. That's how sensitive the controls are. They're like nanometers or whatever. Now, when you get such an extreme control system to take out all the motion of everything, we've measured that it damps everything so well that those mirrors get to a ground state motion that's equivalent to 77 nano-Kelvins. There's in this dimension, there's hardly any motion. And they don't freeze. It's what their effective motion is. So that's how much we've isolated them from everything around them, which is very impressive because they're bolted to the earth, right, with suspensions. So isolating from the earth is a real challenge. Other extreme things. We use ultra high vacuum, 10 to the -9 to 10 torr, which is more extreme than outer space. But what's really extreme is how much of a volume we have. Well, the volume we have is basically the same volume as the CERN Super Collider's pipe. It's the largest volume on Earth at ultra high vacuum. In fact, we have parts of our tube, and our tube that goes out along the arms is 1 meter across, 3 mil stainless. Those arms have not been up from vacuum for almost 20 years. Which is a good thing, because if we popped a hole in there, it would take us 2 years to pump them back down. So we're a little insanely crazy about our vacuum system and valves. So that's how extreme the LIGO interferometer is. But when you do extreme things, instruments, you can do extreme astrophysics. Here's our latest catalog from what we call the stellar graveyard. We got about 90 mergers, mostly black holes, but some of them are neutron stars. We've seen 2 or 3, and those are really great because other telescopes can see them. We've even seen odd things where it's a neutron star and a black hole, and we're rewriting a lot of science because we're seeing things a lot of theorists predict, well, you shouldn't see anything in that mass range. And we're like, au contraire. We saw it. You're going to have to rewrite your dang theories. Sorry, our bad. So that's after our initial runs, and we've been ramping up in performance. But I do want to talk about this neutron star. The reason this is interesting, almost all the events LIGO sees, LIGO and Virgo are the only instruments that can see it. So you can imagine there's a lot of convincing to tell people like, sure, you saw those black holes. Sure. No one else saw them. How do I believe you? Well, the belief was finally said is we saw this binary neutron star that was pretty close. And when we predicted where it was with LIGO and Virgo, the gamma ray observatories, Fermi also saw it a couple seconds after we saw it. And then the optical telescopes went in and said, yeah, we can figure out, go back in the plates, and yeah, there's a big thing that went. Neutron stars have an optical thing. You can see them in telescopes and X-rays. And so they could see them. So we said, good, you finally believe us now when we tell you we're seeing something. But we could do some really great stuff with that. One thing is, I want to impress on you how different gravitational wave detectors are versus regular telescopes. electromagnetic telescopes that you're familiar with, big dishes, things like that, you can focus photons, you can focus light. So they're very good at angular resolution, but they're really bad at measuring distance. They can tell you it's over there, but they can't tell you where is it, how far is it. And so they have a very complicated scheme of Cepheid variables and various things. They know how much they should have in absolute brightness. And so it's very complicated to measure something called the Hubble constant, which is how fast is space expanding. There are two main measures they've done. They don't agree at present. The error bars don't overlap. Now, gravitational waves can't be focused. And so we don't have much directionality. It's not a dipole. It's almost uniform in distance. We use timing. So we have to use like your ears to tell you if you've multiple detectors. So it's the speed of light delay tells you which way is it coming from. So we have poor angular resolution, but we measure an entire waveform. The waveform, gravitational wave waveform, as the things go together and go smack and go down. Because we measure all that, and general relativity tells us, well, the ups and downs of that tells you how big the thing was. Well, then we just say, well, how high is that? Not the shape of it, but how much the apparent intensity is. We're great at measuring distance. Every collision tells us how far away it was. So we're great at measuring the Hubble constant. And we'll get better. And here's a comparison. Latest measure from LIGO. If you look at this plot, you'll see that there's the Planck and Shoes are the two optical optical measurements, and they don't agree. Those are like error bars. One says, oh, about 76. One says, no, it's like 68. But then even from our first neutron star, the black one, we could measure it. And now we can take our black holes, add them all together, and the blue is the latest one. So we're getting competitive. We're favoring one particular measurement, but there's an uncertainty there. So we hope when we get more, we may help resolve this whole issue. So, okay, told you all about our great discoveries. We'll be doing more, but I want to switch gears now and tell that we do hacking too. Just to let you know, not the only ones. Why do we do this? The LIGO staff is quite so. The lab itself only has like 180 people. We have a lot of customers, but there aren't that many people working in the instrument, but they're very clever people. And we're always solving novel problems not seen elsewhere. There's no Acme interferometer company you can order stuff from. And because we're doing taxpayers, we use a lot of off-the-shelf hardware as much as possible. And so to make the precision, we've had to do several hacks. I'll give you a few examples of those. We've had to do software hacks, electronic hacks, mechanical hacks, and quantum mechanical hacks. Okay. And I like to do this because I don't really get to talk about this much. So what was the first software hack? And Rolf Bork and Alex Ivanov came up with this. I just use it. Okay, the real hack was, how do we do hard real-time computing? And what does hard mean? Well, first, why do we have to do it? We use what's called digital filtering to control the interferometer, feedback loops, high-pass filters. So you're running at a certain frequency and sampling the data. Okay, we've gone with off-the-shelf computers so we can change rapidly and ride Moore's law to faster performance. We used to have very custom computers with insanely expensive compilers and stuff like that. But Linux was coming on recently. So now the standard real-time operating systems, real-time Linux, things like that, they're pretty good cycle times, but they have this tail. And the tail is what kills you. There's a long tail of rare cycles up to 1 millisecond. The problem is the LIGO control loops have to go from reading an A to D converter to outputting a D to A converter for the control at 64 kilohertz, at 16 microseconds. And we can't run long, that is skip a cycle for days. So that's hard real time. So the question was, how do you do that? Okay. We use a trick. The trick is, run your code on one of the idle CPUs. Now that you have computer CPUs with multiple cores, you can flag one of the CPUs as idle. So the OS won't use it because you're saving energy. But the trick is you load your core as the idle loop on that processor. I mean, it's powered up. You haven't turned it off. You're running. It's just the OS doesn't know you're there. And you don't get interrupted. If you work hard, you have to work very hard to turn off all the interruptions. In the original hardware, we had to turn off. You can't let the computer slow down. None of that energy savey stuff. No hyper-threading, no turbo mode. We had to turn off the USB ports on these things, PS2, because that generate interrupts. And you have to tell the operating system, no, don't knock on the door to see if we're awake or not. So we got that to work. And it's interesting when you did that, because we were doing that and we were using PCA bus reflective memory for co-located to exchange data between computers. And we were using GPSs. And when we came up with this, we were asked to talk to a bunch of Linux gurus in Germany. I'm like, why is that? Then we found out the other people who want to do something this extreme. Fast stock traders. So I sort of feel bad that after we show them this trick, that we're going to be the responsibility for the next flash crash. So that's the trick we've used. Now, and you make the software very simple. It isn't one of these multiple loops with threads. Single thread is very simple. All it does is it sits waiting for a trigger that the ADCs have new data, reads the data, updates all the filters, puts stuff out in memory for the D-to-A converters, and just goes back to the top. That's all it does. Very simple. Now, it has to do other things like put out data for other things, respond to user inputs. And so what you do is you spread those in tiny pieces across the 64,000 cycles per second, small enough so no time does it exceed your 16 microsecond time budget. You have to run in kernel mode, which means you can't do those nice math libraries. If you want math, you got to write yourself. And you can only communicate through memory buffers. So you have to have, and you hand off the memory. And so you use DMA, direct memory access, a lot. So you just put it there and the ADCs, the D-to-A converters pull it out, or the ADCs put it there. That's how you talk to all the other processes you have that aren't real time to talk to users and export data. So it worked. We had another hack, same people. It was, how do you write the code? The amount of control software we're going to need for like 100 different processes, which is way more than the 2 people we had. You can't be sitting there overnight and trying to look at requests from users and write it. But it turns out it's all very similar. It's all got one filter. We use very standard filters. It's all how you package them and run the wire. So it's like a circuit. And in fact, it's a circuit. So if you could write a code generator, if you could get something that described this and you wrote the code based on that description, then you could, if someone just changed the description, it would write the program. But people want to write down, but what you really want is a graphical one. That is, you want the users to write the code for you so they can draw it out. And okay, you could write your own graphic package and do all that. But we were already using MATLAB because it has all this great stuff for digital filtering. So, but it had this other thing called Simulink, which we didn't really use. It sort of wasn't working well, but it's a great drawing package. So if you make your own parts be the filters, you put them in the diagram, and you write a parser for that file, you use that to build the code. So you save yourself writing your own graphics package. And we've used that. And so now the users can change the code whenever they want. And all the programmers do is maintain the code generator. They don't do the individual programs anymore. Those are 2 big software hacks. So typically, here's part of one, or typically complicated. So they drew all this and you parse it. And they can put comments and lots of crazy colors. So, but they also documented it. So those are software hacks. We had to do electronics hacks because the major problem we have is noise, electronic noise. Anything that is there, persists for a while, will show up in our data. So we have to eliminate a lot of noise. So things we did like Switching some power supplies, you got to use linear DC supplies. And then we even put them like 50, 80 feet away in another room. So you can't see the switching noise on the digitizers. The computers that you have running flat out are noisy as heck. Oh, they're in yet a different room and use a fiber interconnect to connect to where the digitizers are. But there's even more subtle things. We find out that you often want to synchronize your digitizer. So you have a clock signal going into one ADC. You read the edge, sharp edging edge, you're all locked. You can't do that. You have a sharp edging edge in one of these ADCs, they're synchronous ADCs, you pick it up on the other channel and you screw up everything. So you can't have sharp edges. And so, because everything's you're doing analog, you're taking analog stuff, digitizing it, putting out back analog. So what you do instead is you make something called a duotone. You have two oscillators at 960 hertz, 961 hertz. They have 1 hertz beat signal. You fit the waveform to figure out where it crosses at the beginning of the second. And that's what you use for your 1 pulse per second timing signal. And then we were finding that we were getting 2 hertz and ½ hertz signals. And they were because there were LEDs, nice blinking LEDs telling you the timing system is locked. Well, but they're running all the time and they pull down the ground plane and you pick those up. So in one case, we changed the code. So when it's happy, it's constant. In some cases, the vendor says, no, they're going to be that way. That's how it is. So you just pop the LEDs off, little surface mounts. Another thing is we had photodetectors. So we're trying to pick up infrared light and we weren't big enough to get ultra custom infrared photodetectors, but you can make a infrared photodetector pretty easily. You get the can that the photodetector's in and there's a lens on it, optical, you cut the lens off. So your engineers get very good at cutting lenses off photodetector cans. Okay, then we have some electromechanical hacks. A fast shutter. Remember I told you there's a lot of power there? We were finding out when we would lose the lock, the power goes somewhere. We found it was burning holes in the substrate of the photodetectors. So we needed a vacuum shutter. Now it had some requirements. It had to go 6 millimeters in 1 millisecond and block 45 joules of energy. Now going 45 seconds isn't so hard. 6 millimeters, that's like an arm on a disk drive. We started looking at those to begin. But you had to be a little beefier because of the 45 joules of power. And so they came up with this thing that bounces up. I'm going to show this little video. And you'll see it goes, should trigger, go bounce up. Okay, now that's really slow. Well, that was because we used, now to get that video to make sure it was moving fast, okay, we did have to use a $500,000 camera to do this video, but it did work. That's what you're doing here at Caltech. Someone's got one of these cameras. So you have to design one of those gizmos. And that gets us to mechanical hacks. We have to fight vibration. We see all these signals, we seismometers, pretty much all the data that we do from LIGO is to tell us that it's not a gravitational wave, that it's a passing truck, that we see that the truck moved and it got into the interferometer and things like that. And so we have all these seismometers around and we're trying to figure out what the problem is. And we are finding a particular signal at about 30 hertz. And Anna Maria Effler and Arnaud Pele found this. It's use seismometers and you like turn HVAC on and off and what is causing it. And they isolated it. And you'll see this picture here. Now the graphic shows it before and after. You see this picture, that's a spring-loaded mount for an HVAC fan. Now, you may see that circle thing. Now, you may think that's a rock. That's a mechanical short, if you ask a mechanical engineer. Okay, it's a rock. So we had to find those. Another mechanical hack, we have to damp things that are flexing. And so you have this thing that's vibrating, you're picking up that vibration. So you want to have like a tuned mass damper or semi-tuned. And so there's a lot of creativity. It's got to be in vacuum. And so one mechanical engineer came up with all these designs of different pieces of Viton with cable ties of different designs that would work. And much testing, he said the poofy hat worked. And now the Hawaiian, hat sort of worked, except it probably drooped. So yeah, we don't use cable ties, use something ultra vacuum. Brian Lance came up with this. So that's one of our hacks. So another one was CryoBaffle dampers. Recently, you have a baffle to baffle light, but it's inside the tube and it's bouncing around, and you have something called eddy current dampers for the slow stuff, but not impulses. So what do? Well, you get more squidgy bits and you put them like back up against each other to keep the thing from bouncing. Arnaud came up with that one. And the final one are acoustic mode dampers. It turns out we had a problem that the mirrors do vibrate, like the drum modes. And if that frequency is the same as a resonant frequency for the optical system, you get runaway, amplification, parametric instability. And we had a whole system to do that. But then a really clever mechanical engineer, Sebastian Biscan, came up with, use tiny little piezoelectric dampers designed for that frequency range, and they oscillate the other way to help dampen. And here it is, this tiny little thing glued on the side of the big mirror. And the only difficult part is you wanted to make sure it didn't fall off. So it was you had to go in there and like push it and glue it on and make sure you have glue that's not going to come off. So last hack, quantum hack, squeeze light. This is our noise curve. It's logarithmic in frequency, logarithmic in strain. And it has pretty much all these curves have something at the lower frequency, sometimes 1 over F noise, but it's a combination of things here. And then it goes up at high frequency. And that going up at high frequency is often called shot noise, Johnson noise. It turns out that's a quantum effect. The effect is that because light is quantized, oh yeah, Einstein said that too. Because it's quantized, as you go up in frequency, there's only so many photons. And so you have smaller and smaller boxes when you're measuring the waveform for a photon to be in. So depending how bright the light is, you don't digitize it too well. So you have big uncertainty in the intensity or the phase. And so this is it limits how well you can measure things. And so it's only limited by how much power you can use. And now this other thing called radiation pressure at low frequency, but we'll worry about the shot noise. And so you can fix it by cranking up the laser, but you crank up the laser, light now bounces everywhere, it gets back in, screws you up. So what you really want to do is beat that shot noise, push down without raising the laser. So how do you do that? You do that, if I can get this to go. Okay, so I want it in advance. Okay. All right, let's try this. There we go. Okay. Now these vacuum fluctuations, and here it's getting a little deep, so I'll try and make it quick. This quantum noise is actually from quantization of the electromagnetic, something called a 0-point fluctuation. But the important part to note is it's the Heisenberg uncertainty principle coming in here. The things we want to measure out this light is the amplitude, how big it is, and the phase, where does it go up and down? And in fact, in this thing, we really care about the phase because that tells us how long the arm is. Now, in normal uncertainty, you have these two variables. The joint uncertainty of them has to be greater than some sun. So you get this circle between x1, it's between phase and amplitude. So circular. And so on average, you can never get better than a certain precision in phase or in amplitude. And so that sets the limit for shot noise. But what if it isn't a circle? And so what the hack is you use something called squeezed vacuum. Yes, it's getting pretty deep here. But the important part to you is we take the light, basically measure how the light's going back and forth, and we rotate the uncertainty. So it's no longer symmetric. Then in fact, we take this, the area has to stay the same. So we squeeze it so that all the uncertainty is in the amplitude we don't care about, but there's much less uncertainty in the phase, which is what we do care about. And so when you do this, you can beat and improve by several dB, 6 dB or so, that uncertainty. So that was our quantum hack. So that brings me to the end of my talk. But I just want to say thank you very much. I'll take this. I think we want to maybe have some questions after this. So let me stop my share.
Spectacular presentation, Keith. Thank you so much. So we have a ton of really good questions in the channel, and I'm going to get to those, but I have one on my mind that I'm not really able to reconcile. Can you describe like the speed of the gravitational waves? Like I know you run the installation for a long period of time.
Okay, that's actually a question. And one thing I didn't put in here is a lot of things that we said about general relativity by measuring these gravitational waves. And the one thing we did with that neutron star detection is the speed of gravity is the speed of light. There's a lot of alternate theories about general relativity. They say it goes faster or smaller, but because we saw the signal with our detector and the gamma ray burst people saw it like a second or two later, basically over that great distance, gravitational waves move at the speed of light. And I improved it, which actually threw out a whole bunch of crazy theories people came up with. Does that answer your question?
Yes, absolutely.
It's at the speed of light, like everything else.
Another one, these are in no particular order, but they are all interesting questions. You mentioned putting the test masses, making them extremely cold, and isolating.
They act like they're cold. We aren't actually freezing them. That you've reduced their vibration so effectively, but you aren't actually like chilling them. So they say as if it had the amount of residual motion of 77, as if they were that cold.
Right. And then
it's mostly because we're damping them.
Yeah, and isolating from seismic effects. So you showed some of the dampening for that. But the question is, do you have to account for Earth's motion?
Oh yeah. What we have to adapt for the tides, believe it or not. That the tides move stuff. So we actually have a slow loop that adjusts for the tides, adjusting our thing. So we don't have to, the Earth, so it's mostly the tides we have to correct for. So we have a loop, a very slow loop, for every 12 hours that adjusts the tidal motion that affects the length of our arms. So yes, we don't have to correct for the Earth itself, but for these effects from the tides.
That is wild. Let's see. You mentioned damping the mirror, and there's a question on that a little bit. So the question was actually on the runaway amplification mode.
Right. It's okay. What's happening is there's optical frequencies in the interferometer, and you get energy in that. And the problem is if they're over here, then you can damp them with one way. But then you have a physical mass. And physical masses have drum modes. So they go like this, and they go like this, and that. And if the mechanical mode lines up with the optical mode, as you heat the thing up, and that's what amplifies mechanical mode, you cranked up the laser, then it's right at the optical frequency. So the problem is that you can't damp this optical one anymore because you're hitting it with the mechanical. So there's various things you can do. If you heat you can change the temperature with heaters of the mass, and so they don't overlap anymore. But in some cases you can't. So it's called a parametric instability because it's a runaway feedback loop.
This one is a question on the waveform. So the question is, I didn't quite get how the distance is embedded in.
Well, the way the distance is embedded is you do the theory, if it's this big, the waveform, it's the variation of how it goes up and down and the time. Okay. So I could show, but basically if it's more massive, it takes longer. And we do the fits. We measure the waveform. Well, for neutron stars, we measure for like 20 minutes. but we measure it for a second or so. That extended waveform, if you solve what equations, what will it look like when it goes together? What will it look like? And it's the ratio of how fast it goes up. Does it have some extra bits in it? How long is it between each part in time? And the relative heights. And that, when you solve the equations, that will tell you that was like a collision of 30 solar mass star with a 10 solar mass, black hole. And either they were spinning or not, you can have some information on that. The more precisely you measure that, the better you do. So it's the shape and timing that matter. And then the absolute signal you see here at the Earth tells you and when you do the equation, it tells you where it occurred, what the absolute magnitude is, which is way more than here. But then how big is it when it gets to here? And by that 1/r, that tells you how far away you are, how much it's decayed away.
Another good question. The hard real-time system that you were talking about, is that available? Is the code for that available?
It's actually quite simple code. I think we've put it on our remote code. We've just put it on git.ligo.org. I think it's mostly public now. It's actually pretty simple. You just put a hook into your code. But yes, it is. We've been trying to make all our code public, not just because but we're going to be working with people in India and whatever. And so, yeah, there's a git.ligo.org, and I think there's a public part of it.
And we'll work on putting a link to that in the.
Yeah, we can do all that. We're trying to make it also. We have a lot going on with packaging, so it's much easier for people to install it for test stands and things. The other piece you have to do is these memory buffers, because you have to put things in. So there's a lot of tricks, but it's all in there. But yes, we are trying to make it all public. I think we currently use a custom version. We take a modification of a real-time patch to Debian 10 right now, working on 11, but we've used Gen 2 before. Eric.
This is a question about geology, and I actually had a question.
I can do that.
As well, so two things. The first one is, does geology of the location of LIGO introduce things that have to be corrected for? And the other one is, can you talk about that? There was a band on the globe when you were talking about locations, and talk about what that band is showing.
Well, that band was, that band was an uncertainty. I think we can go back to that. But first, geology. Yes, we're in a swamp. And so, and we're close to the ocean. So in fact, we had to put in more seismic isolation here at our site in Louisiana to damp out. We actually were planning it for both sites. We actually put it in here early. So where your site is matters. It's actually more seismically quiet in terms of ripples from like water and thing in here, but in the high desert of Hanford, they don't have a problem with the ground moving, except for those earthquakes. But they also have a problem with wind. They have a much higher wind velocity. And the problem is wind will take these buildings and tilt them. And so they've even started erecting wind fences on these across buildings so they don't tilt. So now below you, it's pretty simple. Geology does affect you. Part of the low frequency problem is you aren't on a flat Earth. The Earth is curved. And so as you go to low and low frequency, you're probing farther and farther distances on the Earth in terms of mass, and it's falling away from you. It's something called a gravity gradient. And so because we're on the Earth, that affects our low frequency performance. And I've probably forgotten the thread of the rest of the part. So it's geology. And what was the second half of the question?
Oh, you already had the band on the.
No, the band on there is, it turns out if you only have 2 interferometers, that's why you need 3. You can get an uncertainty, like a ring uncertainty. As you have 2, and you can say it's like here, 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 here. So part of it is you needed to have, I have to go back to, let me go look at that one. There's several bands, but that may have a different band. I remember that graphic.
I think it was the Neutron
Stars.
Stars.
Well, I can describe it. Okay. That was actually an uncertainty from 2 instruments.
Ah, got it.
So that was not actually LIGO. But we do have, that's why we need 3, because you have 2, you can get an uncertainty. And so you need a 3rd instrument to say, you know, and you get something here, but like you can't say if it's down here or up here. So a 3rd instrument refines it. That's why you really need multiple interferometers. But I think that one was because they only had 2 instruments and they could tell a distance. And so the ring was the where on the cosmic. Actually, it wasn't the Earth. That was actually a picture of the celestial.
I'm going to combine 2 different questions here because they're kind of deal with shielding. So one of them says, you know, you mentioned the computers are in another room. Are these shielded with copper tape or something more exotic? And the other question is there anything specific with electronics to protect against cosmic rays and electromagnetic radiation?
Yeah, there's been some thing of that. We don't do too much copper. I mean, what we do is we use linear power supply. So you have a big like locomotive cable, right? So you want to reduce that. That's for the DC power. The thing from the computers is there's electronic noise, but it's actually acoustic because they're running flat out. And in fact, we have racks of electronics that are somewhat near the interferometer. We've had to put, it's not just the electronic noise, it's the vibration doing the concrete slab that's separate, but it gets transmitted through the foil. And so we put in rubber things that are just the right, so they aren't compressed and they aren't just rocking, just enough so they damp out this vibrating rack of electronics. I'm not sure I answered that question, but the copper, I'm not sure where the copper would come in.
Like putting computers in another room and then shielding the room, I think.
Oh, yes, we have thought of, we are going to do this. What we're going to do, we think we've got the noise of one of our most critical digitizers. We're actually going to try that. We're actually going to put it in its own box and try to making a Faraday cage is actually very hard. If there's any aperture, the waves will find it in. It's really hard to make a foolproof Faraday cage.
I would like to give you some feedback in saying that you were wondering if the hacks would be well received, and someone was asking about quantum squeezing before you got to that, and then they're like, yes, quantum squeezing, yes. I love it.
Yes, and so, and we're doing a little more now. The little detail, because I didn't want to take up time, that squeezing that I showed you is frequency independent, it's the same. And it turns out that what happens is when you squeeze at high frequency, it helps the high frequency, but you don't get something for nothing. And so the problem is high frequency gets better, but low frequency gets worse. And it is sort of impinging on the low frequency. The way you can solve that is by having another resonant cavity that rotates it so there's no squeezing at 0 frequency and full squeezing at high frequency. But to do that, you have to make a 300-meter long cavity with a vacuum tube this big. So we're doing construction right now to go out, 1,000 feet out across the swamp with concrete and a thing to make another optic there. So that's part of what we're doing for why we're down is putting in this enhanced squeezing so that we can squeeze much harder at high frequency, but without affecting the low frequency, getting this back reaction.
I really enjoyed hearing about your software hack for connecting MATLAB up to
it'd be nice if they stopped changing the file format. They're almost I think they were it wasn't so bad. They went to XML. We haven't, I think we're going to have to figure out how to parse their XML because they've changed, but that's what happens when you aren't writing this software.
Other huge giant amazing installations that are looking to have an interface for the scientists, what has the feedback been from the people that are using that system?
They're familiar with Mac, so it's great because we also make it so they can generate the software. They just design it. We give them here's how you build it, here's how you make it, and they just do it. And here's how you restart the DAC, otherwise known as don't call me. Here's how to do it. You can do it. And they think it's great because they go in, they change it. Oh, I want a different thing. I want to add these things. They add that in, they rebuild it, they restart it. Now, Other places use Virgo. The one in Italy uses digital signal processors. But of course, it's a much smaller community that can write those. And so you don't quite have the same ability to do it. No, though it's outsourcing code creation is a wonderful thing. But no, I don't think we could have done it without it, because there's just, let's say you have 30 scientists doing it. You'd need an army of programmers, right? And they don't have to write any software. They occasionally write some C code for some special thing that they want to do, but pretty much it's just wiring.
So I think just one final question, and when you were talking about the laser and you said you had a 40-watt laser, off-the-shelf laser, and
no, it's a very custom design laser. It's actually the current one. It comes from an outfit in Germany called Neolaser and Hanover, and we're doing our latest one. It's actually a series of lasers, and in fact, it starts with one, and then we have pumped light that goes in water-cooled things over to a room, and it goes to an amplifier. So actually, the amplifier would get up to 70 watts. And the only reason it's at 40 watts right now is we're having trouble with these mirrors. These mirrors have like 14 anti-reflective coatings, another custom company that does that. But the problem is they get schmutz on them. We have found when they're manufactured, they can get little particles, tiny little ones. They're no trouble when you're illuminating it. When you crank up the power to kilowatts, bang. And so we have bad spots. We've had to steer the light away. And so there's a limit. We can't go above 40 watts right now. But it's actually a series. You start with an N-Pro laser, and then you go through a pump laser and switch it back to infrared, 1024 right now. And then you go through an amplifier, all custom, to get up to actually go 35 watts and then to 70 watts. So yeah, that's all very custom.
Well, this has been such a pleasure today, Keith. Thank you so much for speaking. And I think I speak for everyone. That was a wonderful talk, and we're happy to have had you here. And
I'm glad everybody show all your interest in LIGO. Of course, remember, we have hackers, so we may even be hiring. I think I saw 11 openings last year, 13 openings, because a lot of us are getting old. And so we're, retirement, which is good, but we need new people. So, but it's going to be a little bit, you have to fight against SpaceX and Tesla and all the other great stuff everybody's doing. So, but thank you very much, everybody. I'm glad everybody enjoyed it.